In this video, we're going to look at two examples of word problems that we're going to solve using a system of two equations and two variables. Before I start this example, let's take a look at how we set up a model using a system of equations. There's two main steps to this. First, we want to identify the unknown quantities in the problem, and we're going to assign a different variable to each of those unknowns. That makes the first step pretty easy. Most of the work is going to be in the second step, where we have to come up with a system of equations. Usually it's going to be two variables and two equations. In either case, the equations are going to come from either key statements made in the problem or something that's either assumed or understood beforehand. And then we write a separate equation for each of those conditions. Back to our first example. This is an interest or investment problem. This is a pretty common example of a word problem where we use a system of equations. Ethel invested money in two different accounts. The first one had an annual interest rate of 13% and the second one 9%. We're also told that she had $700 more invested in the 9% account and she earned a total of $239 in interest for the year. The unknown quantities in this problem: how much did she invest in each account? So that's where we start. We're going to assign two variables. X will be the amount that was invested in the 13% account, and Y will be the amount invested in the 9% account. We're actually going to find it useful to set this up in a table. I have one row for each account. The first column shows the amount invested in each account. That's the X and the Y that we defined here. The second column states the interest rate for each account, which we wrote as a decimal. You shift the decimal two places to the left when you drop the percent sign. So we get 0.13, 0.09. And the last column gives the interest earned for the year in each of the two accounts. This is going to be simple interest, so we're just going to multiply the interest rate times the amount invested. 13% of X dollars is the interest earned on the first account, and 9% of Y dollars is the amount of interest earned on the second account. This table is going to be useful because it's going to help us set up our equations. In every one of these examples, one of the equations is going to involve the amounts invested, and the other equation is going to involve the interest earned on each of the two accounts. Notice the two key statements that we're given. I've identified them here and underlined them. The first one says that she had $700 more invested in the 9% account. That's a statement about the amounts invested. The second statement says that she earned a total of $239 in interest. That's about the interest earned. So let's look at how we set up those two equations. Taking the first key statement here, she had $700 more invested in the 9% account. I want to try to write that in a form that's more direct, easier to translate into an equation. What that line is telling us is the amount invested at 9% is $700 more than the amount invested at 13%. If you look at the comparison they're making, the 9% account had $700 more invested in it. Writing it this way, it's easy to translate into an equation. The amount invested at 9% is just Y. The amount invested at 13% is just X. So this is saying Y is 700 more than X. Y equals X plus 700. That's the first of our two equations. The second key statement, she earned a total of $239 in interest for the year, tells us that the total of these two amounts is $239. So this is the sum of the two amounts from the third column equals 239. So that completes our model. We have our system of equations. Let me show you how we solve that. This was everything I just showed you. So we ended here with our system of equations. We need to solve this, and we can use any of the methods we like. This system is set up nicely for substitution because the first equation is already solved for y. So I'm going to substitute that into the second equation. You can see that up here. Here's the second equation. I replace the y with x plus 700 from the first equation. Distribute the 0.09 to the parentheses. 0.09 times 700 is 63. Combine our like terms here. Subtract 63 and divide by 0.22 on both sides to get x equals 800. And once we have x, we can plug back into either of these two equations. The first one's obviously easier here, and we get y is 800 plus 700, or 1500. We do not want to leave our answer in terms of x and y. We want to go back and answer this question in words. How much did she invest in each account? $800 was invested at 13%, $1,500 invested at 9%. Before we go on to the next example, let me just remind you that you're going to have one equation that involves the amounts invested and one equation that involves the interest earned from each account. In my experience, there's two types of equations. You're either told the total value of one of these columns. In this example, we were told that the total interest earned equaled $239. You could have that for the amounts invested also. You could be told the total amount invested and have x plus y equals some number. And the other type of equation is similar to this first one here, where you're told that one of the amounts is more or less than the other by something like 700. You could have one is 500 less than twice the other. Some sentence that needs to be translated into an equation. And you could have that for the amounts invested or for the interest earned. You could be told the interest earned in one account is, say, $100 more than the other. So you really need to understand what these expressions represent in the problem, and you need to pay close attention when you're reading these key statements and make sure you know whether they're talking about the amounts invested or whether they're talking about the interest earned. Now we'll move on to our next example. We're going to look at a mixture problem. This picture just shows a very simple example. I picked antifreeze because I think it's fairly common and people are familiar with it. The coolant in a car is a mixture of antifreeze and water. Usually it's 50% antifreeze, 50% water. So let's imagine that we have one batch of coolant that's 50% antifreeze and another that's 60% antifreeze. We call those solutions. And if we mix 10 gallons of each, you can see that we're going to get 20 gallons altogether in our mixture. And it's pretty obvious that the concentration of the mixture is going to be somewhere in between the original two concentrations. If you're mixing equal parts, then it'll be exactly halfway between those two. It'll be the average of the two percentages. For the word problems, this concentration probably won't be halfway between these. And we'll have to figure out how much we need to add of each of these two solutions to get the appropriate concentration in our mixture. Two things to notice about this. The total number of gallons in the mixture is the sum of the amounts of the two solutions. 10 plus 10 equals 20. And if you consider the amount of antifreeze in each of these solutions, 60% of 10 is 6 gallons, 50% of 10 is 5 gallons, and when we add those together, we get 11 gallons, which is 55% of 20. So we're going to get two equations from that. Let me just organize this information a little bit so it's easier to turn into a table. I've lined these up in columns to look like addition. So we're adding the two solutions together to get the mixture. And I've shown that when you add the amounts of each of the two solutions, you get the total amount of the mixture. And when you add the amounts of antifreeze from each of the solutions, you get the amount of antifreeze in the mixture. We can put that in a table, similar to the table we had for the interest problems. I have one row for each solution and a third row for the mixture. The first column is the amounts of each of the solutions and the mixture. The second column is the concentration, or the percentage of antifreeze. And the third column is the amount of antifreeze, which is the percent times the amount of solution. Let's see what this looks like now if we put some variables in. Suppose that we don't know how much of each we need to add together. Those would be the unknown quantities. So we would use a variable for each of the unknowns, x and y. And we'll have variables in the third column as well when we multiply the percent times the amount. Let's look at the two equations we get from this. In the first column, the x plus y has to equal 20 for the total amount of the mixture. And similarly for the third column, we add the amount of antifreeze from the two solutions to get the amount of antifreeze in the mixture. That gives us two equations to go with our two variables. And this is a pretty typical setup for a mixture problem when you're using systems of equations. In these cases, you will almost always have two equations like this, where you're adding the expressions from the first two rows and setting it equal to the third, just as we did in these two. If you wanted to solve a mixture problem using one variable and one equation, this would be your one equation, the one where each term is the percent times the amount. And then, instead of having x and y, you would have two expressions that would show the relationship between the two amounts. In this case, since they make a total of 20 gallons, we could just use x and 20 minus x. But in these examples, we're going to stick to using two variables and two equations. Now we don't need to solve this system because we already know the answer. It was 10 gallons of each. I want to show you another example. And we're going to switch to acid solutions, but that won't matter. How many liters of an 80% acid solution and a 50% acid solution must be mixed to produce 24 liters of a 60% acid solution? So we start with the unknown quantities. How many liters of each? We assign a variable to each of those. X will be the number of liters of the 80% solution, y will be the number of liters of the 50% solution. We set up a table, just like the one I showed you. The first column is going to be the amounts of the two solutions and the amount of the mixture. The second column will be the concentration, or the percentage, of acid. And the third column is the product of the percent times the amount to give you the amount of acid in each solution and the amount of acid in the mixture. And we're going to get two equations for this. The sum of the two amounts has to equal the amount in the mixture. That's our first equation for the total amount of the solution. And secondly, the sum of the amounts of acids in the solutions has to equal the amount of acid in the mixture. Now all we have to do is solve this system of equations. Here's the model that I just showed you. Here's the system of equations we want to solve. I've done that over here. This looked like a nice example to use the addition method, or the elimination method. I thought it was easiest to eliminate the y, so I multiplied both sides of the first equation by negative 0.50. So negative 0.50 times equation 1 gives me negative 0.50x, negative 0.50y, and negative 0.50 times 24 is negative 12. Leave equation 2 alone. The y's will cancel. Combine my x's, divide by 0.30 on both sides, and that leaves us with x equals 8. And of course it's going to be easiest to plug that back into the first equation to get y equals 16. So 8 liters of the 80% solution, 16 liters of the 50% solution. That answer seems reasonable, although of course you can check the solution in the system of equations to make sure it's correct. By the way, if you prefer to eliminate the decimals, I chose not to here. I think if you're using a calculator, it's just as easy to keep the decimals in here. If I wasn't using a calculator, I would probably eliminate the decimal just to avoid any mistakes when I multiply or divide and getting a decimal in the wrong place. Here's what it would look like if you eliminated the decimal. Shifting the decimal 2 places to the right is the same as multiplying by 100. So we multiply both sides by 100. And of course you really could have shifted this 1 place because of the zeros here and multiplied both sides by 10. Either way, it's going to look pretty similar. The remaining steps are going to look almost identical to what we did here. Let me just end this video with one little variation that you might see in these types of problems. Let's say you have 5 gallons of 25% antifreeze, and you want to add pure antifreeze to that until you get a 50% antifreeze mix. This is a little bit different because now we know the amount of one of the solutions. That gives us an unknown for the first solution, which is the pure antifreeze, and another unknown for the mixture. Another interesting thing is that pure antifreeze has a concentration of 100%. So when we write that as a decimal, we get 1.0. And multiplying that times x for the amount of antifreeze just gives us x. This is pure antifreeze. So the amount of the solution is the same as the amount of antifreeze. 0.25 of 5 gallons is equal to 1.25, and for our mixture we have 0.50 of y gallons, 0.50 y. So we get the same two basic equations that we had in the last example. We just have the variables in different spots. If you want to see what the solution to this example is, I will leave you with this. I used the substitution method to solve it, and here's the final answer.